minus 290 degrees Fahrenheit. That is the temperature on Titan right now. At that temperature, every lake, every river, and every raindrop on Earth would be frozen solid. And yet Titan has weather, not the occasional breeze or drifting frost, but clouds, rain, rivers, coastlines, vast seas, and changing seasons. It is the only world beyond Earth where scientists have found an active landscape shaped by flowing liquid. The difference is that none of those rivers carry water. They carry liquid methane. Titan is Saturn's largest moon, wrapped in an atmosphere thicker than Earth's and composed mostly of nitrogen, making it the only moon in the solar system with air dense enough to hide its surface from view. When the Cassini spacecraft finally pierced that orange haze, what emerged looked strangely familiar: branching river channels, shorelines, sand dunes stretching for hundreds of miles, a world that seemed to follow many of the same rules as Earth while operating with entirely different chemistry. Beneath its frozen crust, scientists also found evidence pointing toward a hidden ocean of liquid water sealed away beneath miles of ice, a place that has become one of the most intriguing destinations in the search for life. But if Titan resembles Earth in so many ways, why would a human survive there for only moments? What keeps its methane seas from disappearing? What did the only spacecraft ever to land there discover during its brief descent through the orange sky? And could one distant moon be teaching us that life does not have to look anything like life on Earth? Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. Let's talk about what we actually know. Long before spacecraft crossed the outer reaches of the solar system, Titan existed in human knowledge as nothing more than a tiny point of light. On the 25th of March, 1655, the Dutch astronomer Christian Huygens discovered this distant moon while studying Saturn through one of the finest telescopes of his time. He could not have known that the faint object before him would eventually become one of the most fascinating places we have ever explored. For nearly 3 centuries, that distant point revealed almost nothing. No landscape could be seen. No mountains, valleys, or plains appeared through even the best instruments. We could only watch Titan circle Saturn and wonder what lay beneath its featureless glow. Then, in 1944, astronomer Gerard Kuiper changed everything. Using spectroscopy, a technique that identifies substances by the light they absorb, he detected methane in Titan's atmosphere. For the first time, we knew this moon possessed more than a frozen surface. It possessed air. As our understanding slowly expanded, Titan grew stranger with every measurement. Its diameter stretches about 3,200 miles, making it larger than the planet Mercury, despite having far less mass. At this moment, it rests roughly 886 million miles from Earth, following Saturn through the darkness far beyond the orbit of Jupiter. One journey around Saturn takes almost 16 Earth days. During that orbit, Titan keeps the same hemisphere facing its giant parent, much as our own moon always shows us one familiar face. If you stood there, Saturn would never wander across the sky. It would remain suspended above the same horizon, an immense companion that shaped Titan long before humanity ever noticed either world. Gravity also behaves differently here. A person weighing 180 pounds on Earth would weigh only about 25 pounds on Titan. Every step would feel unusually light, every jump carrying you farther than instinct would expect. Yet escaping Titan entirely would still demand tremendous energy because its atmosphere clings tightly around the moon. Time itself unfolds at another pace. One Titan year matches one Saturn year, lasting nearly 30 Earth years. Seasons drift so gradually that an entire childhood on Earth would pass before one cycle completed. Throughout those long seasons, the surface remains close to minus 290 degrees Fahrenheit almost everywhere we have observed. Even daylight refuses to resemble home. Titan lies so far from the sun that sunlight arrives roughly 100 times dimmer than it does on Earth. Instead of dominating the sky, the distant sun resembles an exceptionally brilliant star struggling through layers of orange haze. Everything we have just established points toward the same expectation: distance, relentless cold, weak sunlight, and immense age should have left Titan frozen and unchanged. Yet that expectation fails. Across this remarkable moon, weather has continued shaping the landscape for hundreds of millions of years, defying what many of us would naturally expect from such a distant world. Among the many worlds circling the sun, Titan breaks one of the simplest expectations in planetary science. It is a moon. Moons are generally airless or wrapped in only the thinnest traces of gas. Our own moon offers almost no atmosphere at all. Ganymede does not possess one like this. Callisto does not either. Yet Titan wears an envelope of air so substantial that it reshapes everything happening at its surface. Stand there in imagination, and the pressure surrounding you would reach about 1 in 45 hundredths times that experienced at Earth's sea level. That makes Titan's atmosphere denser than every planet in the inner solar system except Venus. Rather than feeling exposed beneath an empty sky, you would find yourself immersed within a deep ocean of gas, stretching far above the frozen landscape. Its composition is equally remarkable. Roughly 95% consists of nitrogen, the same element that dominates the air filling your lungs every moment. About 5% is methane, accompanied by traces of hydrogen, ethane, acetylene, propane, and more than 200 additional organic compounds. These are carbon based molecules, meaning they are built around carbon atoms, the same fundamental ingredient found throughout every known living organism on Earth. The resemblance becomes even more striking when we compare the skies of these two worlds. Earth's atmosphere contains about 78% nitrogen, with oxygen making up most of the remainder. Titan lacks abundant oxygen, yet its overwhelming dominance of nitrogen has long fascinated planetary scientists, because no other body in the solar system shares such a close atmospheric relationship with our own planet. Keeping that atmosphere for billions of years required several fortunate circumstances working together. Titan orbits so far from the sun that solar radiation arrives greatly weakened, limiting its ability to strip away atmospheric gases. Although Titan is much smaller than Earth, its gravity remains strong enough to hold onto heavy nitrogen molecules. Saturn also contributes protection through its vast magnetosphere, a magnetic environment surrounding the giant planet that partially shields Titan from the constant stream of charged particles flowing outward from the sun. Remove any one of these advantages, and Titan might resemble the barren moons beside it. This protective blanket reaches astonishing heights. Detectable atmospheric layers extend roughly 370 miles above the surface, while Earth's dense atmosphere becomes increasingly sparse by about 60 miles. That enormous depth changes the physics of movement itself. Combined with Titan's weak gravity, the thick air creates enough lift that mathematical models show a human wearing broad wings could remain airborne simply by flapping. Flight becomes unexpectedly practical, yet perhaps the atmosphere's greatest achievement has little to do with flying. It transforms an otherwise frozen moon into an active world. Air circulates, clouds gather, winds transport energy across immense distances. Familiar patterns emerge through profoundly unfamiliar chemistry. When you picture rainfall, your mind almost certainly imagines water. Titan asks you to set that expectation aside. What descends from its clouds follows the same rhythm that shaped valleys on Earth, yet it is an entirely different liquid, one that changes the meaning of rain itself. Imagine tracing the path of a single droplet from cloud to ground, then back into the sky again. That repeating journey has sculpted every familiar landscape on Earth for roughly 4 billion years. Oceans supply vapor, clouds gather, rain falls. Rivers carry that water across continents before the cycle begins once more. Titan follows the same choreography, although every step depends upon an entirely different liquid. Here, methane takes the place of water. At Titan's extraordinary cold, methane can exist as gas drifting through the atmosphere, liquid filling lakes and seas, and solid ice locked within certain surface deposits. The chemistry changes, yet the pattern remains astonishingly familiar. Methane rises from broad northern seas through evaporation, cools within the upper atmosphere, condenses into clouds, and eventually returns to the surface as rain before beginning the journey again. Gravity lends the rainfall its own character. Because Titan pulls downward with only a fraction of Earth's strength, each methane raindrop descends more gradually through the dense atmosphere. Computer models suggest individual drops may reach nearly 3/8 of an inch across, making them roughly twice the diameter of typical raindrops on Earth. They drift rather than rush, carried by winds before touching the frozen ground. Those falling drops reshape the landscape over immense spans of time. The channels they carve are genuine river valleys, etched into bedrock through repeated flow rather than imagined similarities. Radar observations from the Cassini spacecraft revealed hundreds of branching river systems feeding larger channels that empty into polar seas. Viewed from above, many of these drainage networks closely resemble aerial photographs of river basins on Earth. If you ignored the chemistry and focused only on their shape, distinguishing one world from the other would become surprisingly difficult. The distribution of rainfall also varies across Titan. Near the equator, precipitation is uncommon. Vast deserts dominate those regions, where towering dunes extend for hundreds of miles beneath the orange haze. Farther north and south, conditions shift. Rain accumulates within broad depressions, feeding lakes and expansive inland seas that have likely endured through countless seasonal cycles lasting millions of years. One detail refuses to fit comfortably within this elegant system. Ultraviolet light, arriving from the distant sun, steadily breaks apart methane molecules high in Titan's atmosphere. Each broken molecule contributes to new chemical compounds that settle onto the surface and no longer participate in the cycle. Calculations indicate the present supply of atmospheric methane should disappear within roughly 30 million years if nothing replaces it. Titan, however, has existed for about 4.5 billion years. Its methane cycle continues today. Some process is restoring that lost methane, allowing clouds to form, rain to fall, rivers to flow, and seas to remain filled across geological time. Planetary scientists have proposed several possible sources, each carrying profound implications for how Titan works. Among those possibilities stands one idea that reaches beyond geology alone, inviting us to consider whether chemistry itself might be contributing to the atmosphere in an unexpected way, while the landscape continues evolving beneath an unfamiliar rain. Looking down on Titan with ordinary cameras tells us almost nothing. The orange haze surrounding the moon scatters visible light so completely that the surface remains hidden beneath an unbroken veil. If you approached from orbit with human eyes alone, the world below would refuse to reveal its contours. Every detailed map we possess came through different methods, each designed to see where visible light could not. The most important of those methods was radar, a technique that sends microwave signals toward a surface and measures the echoes returning to the spacecraft. Those returning signals reveal shape, texture, and elevation with remarkable precision. During 13 years in the Saturn system, the Cassini spacecraft completed 127 close flybys of Titan. Each encounter added another narrow strip to an expanding global map until roughly two-thirds of the moon had been surveyed. As that map gradually assembled, an unexpected geography emerged. Near the North Pole, radar revealed hundreds of lakes surrounding three immense seas. Their shorelines align naturally with branching drainage systems, showing that liquids have flowed across this terrain for immense spans of time. Among these bodies of water lie empty basins known as lacunas, depressions preserving unmistakable former shorelines, where liquid once rested before later seasons transformed the landscape. Traveling toward the middle latitudes, the scenery changes again. Broad plains stretch across great distances with few dramatic interruptions. Rising above them are mountain ranges composed primarily of water ice, reaching elevations of nearly 10,000 feet. Under Titan's conditions, frozen water behaves much like hard stone on Earth. Rivers carve it. Rain wears it down. Cliffs and ridges endure through countless cycles of erosion. Closer to the equator, the terrain becomes dominated by enormous linear dunes. These parallel ridges stand roughly 300 feet high, approach a mile in width, and continue across hundreds of miles of landscape. Their striking organization suggests persistent winds shaping organic particles over extraordinary periods, creating one of the largest dune systems anywhere in the solar system. Another region stands apart from everything around it. Known as Xanadu, this continent-sized bright expanse covers an area larger than Australia. Its reflective appearance differs sharply from neighboring terrain, hinting that it may preserve some of Titan's oldest exposed landscapes. Even after years of study, its exact history remains uncertain, making it one of the moon's enduring geological puzzles. One feature is almost absent. Impact craters appear surprisingly rare. Across most ancient worlds, collisions gradually accumulate, leaving surfaces crowded with scars. Titan displays remarkably few, indicating that erosion, sediment deposition, and perhaps activity deep within the moon continually reshape the ground faster than craters can survive. Among the most intriguing locations is Sotra Patera, a formation containing a pit nearly 5,000 feet deep beside a mountain rising to a similar height. Many researchers consider it one of the strongest candidates for cryovolcanism, a form of volcanism where chilled water and other volatile materials erupt instead of molten rock. All these discoveries came from orbit. Yet only once has any machine descended through Titan's concealed sky and encountered this extraordinary landscape face to face, replacing remote measurements with direct experience. On the 14th of January, 2005, humanity finally crossed the last barrier between distant observation and direct experience. A small probe named Huygens, measuring about 8 9/10 feet across and weighing roughly 700 pounds, reached the top of Titan's atmosphere, traveling nearly 13,700 miles per hour. Everything that followed would become the only first-hand encounter ever made with this remarkable moon. The plunge began in fire. Friction with the atmosphere heated the protective shield to nearly 3,600 degrees Fahrenheit, hotter than temperatures found across much of the sun's visible surface. While the exterior endured that extraordinary heat, the instruments inside remained protected, preparing for the long descent still ahead. Soon the sequence changed completely. Parachutes unfolded one after another, transforming a violent arrival into a gradual drift lasting 2 hours and 27 minutes. Throughout that entire journey, Huygens continued transmitting measurements back toward Earth. It sampled temperature, atmospheric pressure, wind speed, and chemical composition while sending home 350 photographs that revealed Titan from ever-decreasing altitude. Around 25 miles above the ground, something remarkable happened. The orange haze thinned enough for the cameras to distinguish the landscape beneath. Bright, elevated terrain appeared first, deeply cut by branching channels that merged into wider valleys before spreading across a broad, darker plain. From above, the scene strongly resembled a river delta viewed through the window of an aircraft. Scientists examining the images later described the experience as profoundly disorienting because the landforms looked immediately familiar despite belonging to a world governed by entirely different chemistry. As the final parachute carried the probe lower, its descent slowed to roughly 10 miles per hour. Huygens touched the surface gently enough that the ground compressed beneath it before supporting its weight. Mission scientists compared the texture to wet sand covered by a delicate crust, similar to the surface of crème brûlée after the first tap of a spoon. Its instruments continued working without interruption. They recorded a surface temperature near minus 292 degrees Fahrenheit and atmospheric pressure approximately 1 47 times that at Earth's sea level. For exactly 72 minutes after landing, the probe continued returning data across the immense distance separating Titan from Earth. The final photographs revealed a broad plain scattered with rounded pebbles composed of water ice. Their smooth shapes told an important story. These stones had been worn down through repeated contact with flowing liquid, much as river rocks become polished over time on Earth. The channel surrounding the landing site appeared dry at that moment, suggesting Huygens had arrived between periods of rainfall rather than during one. The probe remains there today, resting where it landed beneath Titan's orange sky, nearly 886 million miles from the room where you are listening. Its brief transmission confirmed that flowing liquid truly shaped this moon. Then, 1 year later, new radar observations from the Cassini spacecraft revealed something even more extraordinary. The lakes were not inferred features or temporary pools. They were genuine seas, filled with liquid and stretching across astonishing distances. A map can suggest rivers, valleys, and coastlines. It cannot prove that a shoreline truly borders liquid. That confirmation arrived in 2006, when the Cassini spacecraft directed its radar across Titan's northern polar region and received echoes unlike any it had measured before. Vast areas reflected almost nothing back. They appeared exceptionally smooth, absorbing the microwave signals in a way that solid ground could not. The simplest explanation proved to be the correct one. Titan possessed standing bodies of liquid. These were genuine lakes and seas resting inside natural basins, complete with curving coastlines, sheltered bays, and channels feeding into them from surrounding terrain. Their contents, however, were profoundly unfamiliar. Instead of water, these polar seas consisted primarily of liquid methane and ethane, hydrocarbons more commonly associated with natural gas and petroleum on Earth than with landscapes stretching beneath an open sky. One of the first major seas identified was Ligeia Mare, covering roughly 50,000 square miles It rivals Lake Huron in scale. Far larger still is Kraken Mare, Titan's greatest inland sea. Spanning an estimated 154,000 square miles, it exceeds Earth's Caspian Sea in area. Radar measurements indicate depths greater than 1,000 feet in some regions, while narrow channels and straits divide its broad expanse into interconnected basins. Nearby lies Pungamare, a smaller sea linked to surrounding lakes through branching waterways that reinforce the impression of an active hydrological network. The liquid filling these basins is not chemically simple. Scientists estimate that it contains roughly 70 to 80% methane and 20 to 30% ethane, along with dissolved nitrogen carried from the atmosphere above. That combination changes the behavior of the seas. Ethane lowers the freezing point, alters the fluid's thickness, and slows evaporation, allowing these enormous reservoirs to remain stable across long seasonal cycles. Cassini uncovered another puzzle in 2013. During one radar pass across Ligea Mare, bright features appeared where only dark liquid had previously been observed. Later observations found those features missing, while subsequent flybys revealed similar bright patches in different locations. Researchers gave them the memorable name Magic Islands, although they are almost certainly not islands in the ordinary sense. Several explanations remain under investigation. Nitrogen bubbles may occasionally rise from the seabed before bursting at the surface. Floating sheets of frozen hydrocarbons could drift with changing conditions. Seasonal winds might generate waves large enough to alter the radar reflections. Each possibility matches some observations while leaving others unanswered. No single explanation has yet accounted for every appearance and disappearance. The scale of these seas is difficult to appreciate. Combined estimates suggest Titan holds about 40 times the volume of liquid hydrocarbons contained within all of Earth's proven oil and natural gas reserves. Those immense reservoirs occupy only the visible surface. Beneath them lies frozen water ice forming the moon's crust, and deeper still waits another reservoir entirely, one that remained hidden until years of careful measurements revealed an ocean unlike the methane seas above, composed instead of liquid water concealed beneath the ice. The most remarkable ocean on Titan cannot be seen from orbit. No shoreline marks its edge, no waves disturb its surface beneath the orange sky. Every indication suggests it lies hidden far below the frozen crust, separated from the methane seas above by dozens of miles of solid ice. We have never drilled into it, yet several independent discoveries point toward the same extraordinary conclusion. The first clue came from the way Titan rotates. Over the course of a Saturn year, careful measurements revealed that the moon's outer shell shifts slightly relative to its deep interior by as much as about 36 hundredths of a degree. That subtle motion may seem insignificant, yet it carries enormous meaning. A completely frozen world would rotate as one rigid object. Titan does not. The simplest explanation is that its icy crust floats above a liquid layer, allowing the surface to drift independently while the interior follows a different rhythm. A second clue emerged through Saturn's relentless pull. As Titan travels around its giant parent, gravity repeatedly stretches and relaxes the moon, producing a gentle tidal bulge. Cassini measured that deformation with remarkable precision. The bulge proved about 25 times larger than expected for a body frozen solid from surface to core. Computer models consistently reached the same conclusion. A global liquid layer beneath the crust naturally amplifies this flexing, matching the observations in a way a fully solid interior cannot. The third piece of evidence arrived during Huygens' descent. As the probe passed through Titan's atmosphere, its instruments detected a faint electrical signature consistent with a conducting layer beneath the surface. Pure ice conducts electricity very poorly. Liquid water mixed with ammonia behaves quite differently, allowing electrical currents to pass far more easily. Once again, independent measurements supported the same hidden structure. Taken together, these findings suggest an ocean resting roughly 30 to 60 miles beneath Titan's frozen exterior. Researchers believe that this reservoir contains liquid water mixed with ammonia. Ammonia acts as a natural antifreeze, lowering the freezing point enough for water to remain liquid despite temperatures that would otherwise lock it into solid ice. Its location makes the discovery especially intriguing. Beneath that buried ocean lies Titan's rocky interior. On Earth, where heated rock meets liquid water, hydrothermal vents form along the seafloor. These environments sustain entire ecosystems without any dependence on sunlight, drawing energy directly from chemical reactions within the planet itself. If similar interactions occur inside Titan, the hidden ocean may possess a long-lasting source of chemical energy. This discovery places Titan alongside Europa and Enceladus within the growing family of ocean worlds, celestial bodies concealing liquid water beneath icy shells. Yet Titan stands apart from every other known example. It possesses two entirely different liquid environments on the same world. Above the crust lie methane, seas exposed beneath the atmosphere. Far below rests an ocean of liquid water, isolated in darkness for immense spans of time. That arrangement invites an unusually careful question. If either environment can support living systems, could both do so independently? And if something truly exists within Titan's methane seas, what would it consume? What would it breathe? And how different might its chemistry be from every living thing we know? Every beam of ultraviolet sunlight that reaches Titan begins a transformation invisible to any observer standing below. High in the atmosphere, energetic light strikes methane and nitrogen molecules, breaking them apart into highly reactive fragments. Those fragments do not remain separate for long. They collide, combine, and assemble into increasingly intricate compounds, beginning with relatively simple molecules such as hydrogen, cyanide, and acetylene, before growing into far larger molecular structures. Over time, this chemical assembly line produces substances known as tholins. The term was introduced in 1979 by Carl Sagan and Bishun Carey to describe complex organic molecules created when simple carbon and nitrogen compounds are altered by energetic radiation. These reddish-brown materials are responsible for Titan's distinctive orange appearance, tinting the atmosphere and gradually settling across the surface below. Tholins have no natural equivalent on modern Earth. Our planet's oxygen-rich atmosphere prevents this kind of chemistry from unfolding on a global scale today. Yet many researchers believe the young Earth, before the emergence of life, possessed atmospheric conditions capable of producing remarkably similar compounds. In that sense, Titan preserves a style of chemistry our own world may have left behind billions of years ago. Laboratory experiments have made that comparison even more compelling. When scientists mixed artificially created tholins with liquid water, something remarkable occurred within only a few hours. The reactions produced amino acids, the molecular building blocks from which proteins are assembled. They also generated nucleobases, the chemical components required to construct deoxyribonucleic acid and ribonucleic acid. Neither result created living organisms, yet both demonstrated that tholins naturally participate in reactions associated with the earliest stages of biological chemistry. Meanwhile, Titan never stops manufacturing them. Fresh tholins form continuously in the upper atmosphere before drifting downward through the haze. They accumulate across broad plains, settle among towering dunes, and gradually blanket the landscape with organic material. Grain by grain, season after season, the moon covers itself in compounds closely related to chemistry that once preceded life on Earth. The original laboratory work by Carl Sagan and Bishun Carre began with a straightforward question about Titan's orange color. By exposing methane and nitrogen to ultraviolet radiation, they unexpectedly created materials that later became central to discussions about life's chemical origins. Decades afterward, the Cassini mission revealed an even greater surprise. Its instruments identified atmospheric compounds whose complexity exceeded anything researchers had previously synthesized under laboratory conditions, showing that Titan's chemistry continues exploring pathways still unfamiliar to us. Occasionally, another possibility enters the picture. If cryovolcanic activity, a type of icy volcanism involving water instead of molten rock, briefly delivers liquid water onto the surface, those freshly exposed pools could mix directly with accumulated tholins. Such encounters unite ingredients widely considered essential for prebiotic chemistry, the collection of natural chemical processes believed to precede living systems. Titan's frozen exterior is therefore far more than an inactive crust. It functions as an immense chemical laboratory operating across an entire world, continually producing increasingly sophisticated organic compounds. Then, in 2017, researchers identified another molecule already present in Titan's atmosphere, one capable of performing a task every living cell must accomplish: building a stable membrane within liquid methane. In 2017, another unexpected discovery emerged from observations made with the Atacama Large Millimeter Array, a network of radio telescopes located high in the Chilean desert. Researchers detected acrylonitrile within Titan's atmosphere, a colorless and toxic organic compound used on Earth to manufacture certain plastics. On its own, the detection was scientifically valuable. Its true significance became clear only after scientists began asking what that molecule might be capable of doing under Titan's extraordinary conditions. The amount present was far from insignificant. Estimates suggested that enough acrylonitrile exists within Titan's atmosphere to produce roughly 10 million membrane-like structures inside every cubic centimeter of liquid methane in Ligaea Mare. That quantity transformed an interesting chemical detection into something worthy of much deeper investigation. At nearly the same time, researchers at Cornell University explored an unusual question using advanced computer simulations. Could acrylonitrile assemble itself into stable membranes while immersed in liquid methane at Titan's surface temperature? Their calculations indicated that it could. The modeled structure remained flexible despite the extreme cold, maintaining stability at approximately minus 290 degrees Fahrenheit, while separating an internal chemical environment from the surrounding liquid. They named this theoretical structure an azotosome. The word describes a nitrogen-based membrane that could remain stable in cryogenic liquid methane, serving a role broadly similar to the membranes surrounding living cells on Earth. Although no azotosome has ever been observed directly, the calculations showed that such structures obey the known rules of chemistry under Titan's conditions. On our own planet, every living cell depends upon membranes built from phospholipid molecules. These molecules naturally organize themselves within liquid water, enclosing the chemistry of life inside microscopic boundaries. Titan replaces both the building material and the surrounding liquid. Acrylonitrile becomes the candidate molecule. Liquid methane becomes the solvent. The chemistry changes completely, while the underlying principle remains surprisingly familiar. A membrane alone does not constitute life. Rocks can possess boundaries. Bubbles can surround empty gas. Yet every known living system depends upon the ability to separate its internal chemistry from the outside world, allowing reactions to proceed under carefully maintained conditions. Without that distinction between inside and outside, biology as we understand it cannot function. Titan appears to possess the ingredients needed for such structures in remarkable abundance. Organic chemistry is active throughout the atmosphere. Energy enters through ultraviolet sunlight and may also arise from tidal heating deep within the moon. Liquid solvents exist in two distinct environments: methane across the surface and water beneath the ice. Acrylonitrile is present in substantial quantities. Hydrogen and acetylene are both available as potential chemical feedstocks. One by one, conditions often considered essential for life continue appearing on Titan, though assembled in combinations unlike anything found on Earth. Then an earlier discovery becomes impossible to ignore. In 2010, two independent research teams published analyses only weeks apart. Together, they described a chemical pattern at Titan's surface that remains unexplained, one that resembles the signature expected if something there were actively consuming its surroundings. By the time Cassini had spent 6 years orbiting Saturn, an enormous stream of information had reached Earth. Across universities and research institutions, scientists examined that growing archive from different perspectives, often without knowing what other teams might discover. Then, in 2010, two independent studies arrived within weeks of one another. Together, they described a pattern that has never been fully explained. The first analysis came from Darrell Strobel of Johns Hopkins University. Studying Cassini's atmospheric measurements, he noticed that hydrogen gas steadily drifted downward through Titan's atmosphere toward the surface. That part matched expectations. What happened next did not. Near the ground, the hydrogen largely vanished. Existing chemical models could not fully account for where it was going. Something at or near the surface appeared to be removing it faster than known atmospheric chemistry predicted. Soon afterward, Roger Clark of the United States Geological Survey published a separate investigation focusing on acetylene. This compound forms naturally high in Titan's atmosphere through reactions driven by ultraviolet sunlight. Over time, it should settle onto the surface and gradually accumulate. Instead, Clark found far less acetylene than expected. The production process seemed to be operating correctly, yet the expected deposits never appeared in the predicted quantities. Something was preventing acetylene from building up. Viewed independently, each result was intriguing. Considered together, they became considerably more interesting because both matched a prediction made 5 years earlier by astrobiologists Christopher McKay and Heather Smith. They had asked a simple theoretical question: if organisms adapted to Titan's methane lakes existed, how might they obtain energy? Their proposed answer differed completely from biology on Earth. Such organisms could draw hydrogen directly from the atmosphere, consume acetylene as an energy source, and release methane as a metabolic byproduct. Metabolism simply refers to the chemical reactions living systems use to obtain energy and sustain themselves. If that hypothetical biology existed, hydrogen near the surface would become depleted. Acetylene would also become depleted. Those were precisely the patterns Cassini measured. The National Aeronautics and Space Administration responded with deliberate caution. Its public statements emphasized that these findings did not demonstrate the existence of life. Several non biological explanations remained entirely plausible. Hydrogen might react with surface tholins through catalytic processes, chemical reactions accelerated by substances that are not themselves consumed. Acetylene could also participate in ultraviolet driven reactions before accumulating in detectable amounts. Both possibilities remain scientifically reasonable, yet neither explanation has been confirmed through direct observation. The anomalies continue to stand as unresolved pieces of Titan's larger puzzle. Years have passed without a mission returning to investigate them at the surface. Since Cassini concluded its mission in 2017, no spacecraft has revisited this remarkable moon. Pause for a moment and consider the collection of evidence before us. Titan possesses liquid methane lakes, theoretical membranes capable of functioning within those lakes, organic chemistry that naturally produces amino acid precursors, and measured shortages of hydrogen and acetylene, matching a prediction published in 2005. If you arranged every clue across the wall of a detective's office, there would be very little empty space remaining. We have carried one question with us across this journey, allowing it to linger while each new discovery added another piece to the puzzle. Titan's methane should not still exist. Every calculation points toward the same conclusion. Sunlight steadily destroys methane high in the atmosphere, breaking it apart into new compounds that eventually settle onto the surface. The process has continued for millions upon millions of years. Physics suggests the atmospheric methane should have disappeared within roughly 30 million years. Titan itself is approximately 4.5 billion years old. Even today, methane still makes up about 5% of its atmosphere. Each moment, ultraviolet light arriving from the distant sun tears methane molecules apart. Those fragments become tholins, ethane, acetylene, and many other complex compounds that drift downward and remain on the surface. The atmosphere continually loses methane through this process. Known chemistry offers no natural way to reverse it at the required pace. Somewhere, somehow, Titan continues replacing what it loses. Scientists have proposed three leading possibilities. The first is cryovolcanism, a form of volcanism in which extremely cold liquids erupt instead of molten rock. These eruptions could release liquid water mixed with methane or methane-rich slush from Titan's interior, supplying fresh methane to the atmosphere. Several surface features appear consistent with this idea, yet no eruption has been observed directly. Another possibility lies beneath the frozen crust. Methane clathrates are crystalline forms of water ice that trap methane molecules inside cage-like structures. Over immense spans of time, these underground reservoirs might slowly release their stored gas. The concept fits many aspects of Titan, although current models require a larger clathrate supply than researchers comfortably predict. The third possibility naturally attracts attention because it connects several mysteries at once. On Earth, methane is produced in abundance by methanogenic archaea, single-celled microorganisms that generate methane while obtaining energy from simple chemical reactions. Many combine hydrogen with carbon dioxide, releasing methane as a metabolic byproduct. Evidence suggests these organisms have existed for at least 3.5 billion years, making them among Earth's oldest surviving forms of life. Suppose, only for a moment, that something broadly similar existed on Titan, the missing methane source. The unexplained depletion of hydrogen and the shortage of acetylene could all become parts of the same story. You can see why the possibility continues to inspire careful investigation. Yet you can also understand why scientists remain cautious. The present scientific consensus has not changed. Titan's methane mystery remains unsolved. No explanation has yet gathered enough evidence to become the accepted answer. That uncertainty is one reason the Dragonfly mission carries instruments specifically designed to study Titan's methane in unprecedented detail. Among them is a spectrometer, an instrument that separates light into precise wavelengths, allowing scientists to measure isotopes, atoms of the same element with different masses. Biological methane and geological methane leave different isotopic fingerprints. If Dragonfly measures those ratios with sufficient precision after its planned arrival in 2034, one long-standing mystery may finally begin yielding a clear answer. For now, the question remains suspended between chemistry, geology, and biology. Before Dragonfly can continue that search, we should understand the remarkable mission that first revealed Titan's hidden complexity and the extraordinary sacrifice that allowed Cassini to leave such a lasting scientific legacy. Long before its discoveries reshaped planetary science, the spacecraft itself began as an ambitious promise. On October 15, 1997, Cassini lifted away from Cape Canaveral aboard a Titan 4B rocket, carrying the name of the very moon that would eventually redefine its legacy. Few could have predicted that one destination among Saturn's many wonders would become the mission's enduring focus. After a journey lasting 7 years and spanning approximately 2,200,000,000 miles, Cassini entered orbit around Saturn on July 1, 2004. That arrival marked the beginning of an exploration unlike any attempted before. Although Saturn's rings, storms, and diverse moons all demanded attention, Titan repeatedly drew the spacecraft back. Out of Cassini's 293 completed orbits of Saturn, 127 included carefully planned flybys of this remarkable world. Some of those encounters carried the spacecraft within only 590 miles of Titan's surface. At those distances, its instruments sampled the upper atmosphere directly while recording measurements impossible to obtain from farther away. Every close approach revealed another piece of an increasingly complex picture. Cassini carried 12 scientific instruments, each designed to examine a different aspect of the Saturnian system. Cameras operating across multiple wavelengths looked beyond ordinary visible light. Spectrometers separated light into its component wavelengths, revealing the chemical fingerprints of distant materials. Magnetometers measured invisible magnetic fields. Dust analyzers examined tiny particles drifting through space. Plasma wave detectors listened for electrical activity, while an ion and neutral mass spectrometer identified the gases surrounding the spacecraft by measuring the masses of individual molecules. Together, these instruments transformed Titan from a distant orange point into a world with measurable weather, chemistry, and geology. Among them, one instrument proved especially important. Cassini's radar system transmitted microwave pulses toward Titan and recorded the returning echoes with extraordinary precision. Because microwaves penetrated the thick atmospheric haze, radar accomplished what ordinary photography could not. Shorelines emerged, river valleys appeared, mountain ranges, dunes, lakes, and seas gradually assembled into a coherent map built one flyby at a time. Across 13 years of exploration, Cassini returned approximately 635 gigabytes of scientific data, including about 453,000 images. Researchers continue examining that archive today. Even in 2025, nearly a decade after the mission ended, New scientific papers continue drawing fresh discoveries from information already transmitted across the solar system. The mission finished collecting data years ago. Its scientific return continues. Eventually, every spacecraft reaches its final chapter. On September 15th, 2017, Cassini exhausted the fuel needed to control its orbit. Mission planners made a deliberate decision. Rather than risk an uncontrolled impact with Titan or Enceladus in some distant future, carrying Earth microorganisms to worlds that may possess environments suitable for life, they guided Cassini into Saturn's atmosphere. The spacecraft plunged downward at roughly 70,000 miles per hour, transmitting scientific measurements until the surrounding atmosphere overwhelmed its systems and the signal vanished forever. Engineers watching from mission control openly wept as the final transmission disappeared. Cassini's ending was chosen to protect Titan, preserving it for the explorers still to come, including a rotorcraft that will one day cross its skies instead of merely passing overhead. Among all the missions humanity has planned beyond Earth, one stands apart for the way it intends to travel. The National Aeronautics and Space Administration did not design Dragonfly as a rover creeping across frozen ground, nor as a stationary lander waiting for discoveries to come within reach. It is a flying laboratory, a nuclear-powered octocopter built to move from one landscape to another beneath Titan's orange sky. That remarkable design became practical because Titan offers an unusual combination of physical conditions. Its atmosphere is far denser than Earth's, while its gravity is only a small fraction as strong. Together, these characteristics reduce the amount of lift required for sustained flight. Instead of struggling against thin air and powerful gravity, an aircraft on Titan can remain aloft with comparatively modest energy. You can appreciate the contrast by considering a helicopter on Earth. Every flight demands constant effort against gravity, while the rotors bite into relatively thin air. Titan changes both sides of that equation. The atmosphere is approximately 45% denser than Earth's at sea level, and gravity is only about 14% as strong. Across the entire solar system, no other world with a substantial atmosphere offers conditions more favorable for powered flight. Dragonfly reflects that opportunity in every aspect of its design. 8 rotors arranged in 4 paired sets provide both stability and redundancy throughout each flight. Each rotor spans roughly 10 feet in diameter. 8 rotor electrical power comes from a multi-mission radioisotope thermoelectric generator, a device that converts heat released by the natural radioactive decay of plutonium-238 directly into electricity without moving parts. This steady source of energy allows the spacecraft to operate through Titan's long days and frigid climate. Current mission plans call for launch in July 2028, followed by arrival at Titan in 2034. The primary destination is Selk Impact Crater, a basin approximately 50 miles wide near Titan's equator. Long ago, the tremendous energy released during the impact melted water ice and mixed it with complex organic material scattered across the surface. Scientists estimate that liquid water created by this collision may have persisted for thousands of years before freezing once again. That history makes Selk especially compelling. It records a place where liquid water and organic chemistry occupied the same environment for an extended period, preserving conditions widely considered favorable for the transition from prebiotic chemistry toward biology. Rather than remaining at a single landing site, Dragonfly will repeatedly lift off and travel between locations, making flights of roughly 3 to 8 miles before settling onto the surface once again. At every stop, it will collect samples, measure atmospheric composition, and examine surrounding terrain using a diverse collection of scientific instruments. Over the course of its planned mission, Dragonfly is expected to cover approximately 108 miles, exceeding the combined driving distance achieved by every Mars rover. Its instruments are carefully tuned to search for biosignatures, measurable features that may indicate present or past biological activity. They will examine amino acids, nucleobases, isotopic patterns within methane and other carbon-bearing compounds, and molecular arrangements that differ from those expected through ordinary, non-living chemistry alone. Dragonfly begins at Selk because that crater preserves one remarkable chapter of Titan's story. Yet the wider landscape suggests similar chemistry has unfolded across countless other places for ages beyond human history. Across Titan's equator, the landscape changes once again. The broad plains give way to an immense desert unlike any found on Earth. Before Cassini arrived, many researchers expected this region to be comparatively smooth, with only scattered geological features interrupting the frozen terrain. Instead, radar revealed sweeping dune fields extending beyond the horizon, transforming expectations of Titan almost overnight. These dunes organize themselves into long, nearly parallel ridges that stretch for hundreds of miles. Many rise to roughly 300 feet above the surrounding ground and approach a mile in width. From orbit, they resemble the great deserts of Earth, yet every detail reflects an entirely different chemistry. Their shape is familiar, their substance is not. The grains forming these dunes are not made of silica sand. They consist primarily of tholins and other complex organic compounds that have drifted downward from the atmosphere over countless ages. With each passing season, sunlight high above Titan continues breaking apart methane and nitrogen, creating fresh organic material that eventually settles onto the surface. Over millions of years, those tiny particles have accumulated into dune systems of astonishing scale. Their total volume is difficult to comprehend. Estimates suggest the organic material stored within Titan's equatorial dunes exceeds all known oil and coal reserves on Earth by several hundred times. Consider that comparison carefully. Every barrel of oil ever extracted, every ton of coal ever mined, represents only a small portion of the hydrocarbons resting naturally across this distant moon. Yet the dunes present another mystery. They extend predominantly from east to west, even though average winds near Titan's equator generally blow from west to east. At first glance, the landscape appears to contradict the atmosphere that shaped it. Careful modeling eventually revealed a more intricate explanation. Saturn itself plays a decisive role. As Titan follows its orbit, Saturn's immense gravity periodically alters wind patterns close to the surface. These recurring tidal effects reverse the direction of near-surface winds at predictable intervals. Over long periods, those stronger seasonal reversals transport sediment eastward, even though the average background winds move the opposite way. No comparable tidal dune system has been identified anywhere else in the solar system. Viewed from orbit, the dark dune fields invite comparisons with aerial photographs of the Sahara or the Namib. The resemblance is striking. Although every grain beneath an imagined footprint consists of complex organic matter that did not occur naturally on modern Earth. Many similar compounds were first created here only after advances in industrial chemistry, while Titan has manufactured them through natural atmospheric processes for immense spans of time. The dunes also reveal that Titan's surface remains active. Impact craters are remarkably scarce across the equatorial regions because the migrating ridges slowly bury older scars beneath fresh layers of organic sediment. The landscape continually rearranges itself, preserving movement even in a place colder than almost anywhere else we have explored. These deserts represent organic chemistry waiting across an entire world. The northern seas hold that chemistry in liquid form, while the hidden ocean below preserves another environment altogether. Above them all, Titan continues changing with the passage of seasons, demonstrating that this distant moon is not frozen in time, but still reshaping itself year after year. Time unfolds differently on Titan. If you remain there long enough to watch an entire cycle of spring, summer, autumn, and winter, you would spend almost 3 decades of your life waiting for the seasons to return to where they began. Titan circles the Sun alongside Saturn, completing one full orbit in approximately 29.5 Earth years. As a result, each season lasts roughly 7.5 Earth years, turning weather into an event measured across chapters of a human lifetime. When Cassini entered the Saturn system in 2004, Titan stood in the midst of northern winter, while the southern hemisphere experienced summer. The spacecraft remained there for 13 years, long enough to witness a genuine seasonal transition. Rather than capturing isolated moments, it documented a world gradually changing before its instruments, allowing scientists to compare one year with the next as the atmosphere slowly reorganized itself. Among the clearest signs appeared above the North Pole. A massive methane cloud system, organized into a swirling atmospheric vortex, gradually reversed its rotational direction as the seasons advanced. Such a transformation reflected changes in the circulation of Titan's dense atmosphere, confirming that the moon's weather responds to sunlight over extraordinarily long intervals rather than remaining fixed from century to century. The lakes changed as well. Rainfall patterns shifted northward, delivering fresh methane into polar basins that had previously remained comparatively stable. Observations showed expanding shorelines and increasing amounts of surface liquid. Meanwhile, the opposite hemisphere began surrendering its reserves. Features identified as empty lake basins, known as lacunas, displayed unmistakable ancient shorelines but contained little or no liquid. Their shapes preserved the outline of vanished lakes, indicating that methane had migrated elsewhere as the seasons progressed. During 2012, another remarkable event unfolded above the South Pole. A gigantic methane storm blossomed across the atmosphere as southern summer approached its end. The cloud system stretched thousands of miles across Titan, becoming the largest convective storm ever observed there. Convective means driven by rising and sinking currents of warmer and cooler gases, much like powerful thunderstorm systems on Earth, although operating with methane instead of water. Taken together, these observations revealed a complete planetary weather cycle. Methane evaporates from the hemisphere receiving greater sunlight, travels through Titan's atmosphere within large circulation patterns, then falls again as rain over the colder hemisphere. Rivers, lakes, clouds, and storms all participate in this slow migration, moving liquid from one pole to the other over many years. Titan's pronounced seasons exist because its axis is tilted by approximately 26 and 7/10 degrees, only modestly greater than Earth's tilt. That orientation allows sunlight to shift meaningfully between hemispheres throughout its long year. Over the course of one complete cycle, the geography of liquid methane changes in measurable ways. Lakes that appear permanent today may become dry depressions 15 years later, while empty basins elsewhere gradually fill once again. You are not looking at a frozen relic preserved since the birth of the solar system. You are watching an active world whose climate evolves at a pace that almost exceeds ordinary human memory, while Saturn's immense gravitational influence continually shapes the moon from far beyond its horizon. Nothing about Titan can be understood without looking outward. Every orbit, every tide, every shifting season traces back to the immense world it circles. Saturn contains approximately 95 times the mass of Earth and enough volume to hold roughly 760 Earths within it. That enormous presence has shaped Titan since the earliest days of the solar system, influencing its interior, its atmosphere, and even the pace of its geological history. Each time Titan completes an orbit around Saturn, gravity squeezes and releases the moon in a repeating cycle. Across one Saturn year, this process repeats 16 times. The effect resembles a hand gently compressing and relaxing a resilient sphere. Although the movement is slight, the continual flexing generates heat deep beneath Titan's frozen crust. That energy cannot melt the icy surface, yet it may provide enough warmth to help preserve the hidden ocean that lies beneath, keeping liquid water from freezing solid over billions of years. Cassini measured this deformation directly. During every orbit, Titan's surface rises and falls by approximately 30 feet in response to Saturn's changing gravitational pull. Such movement would be far smaller if the moon were frozen completely through. Instead, the observations support the picture we explored earlier: a rigid outer shell resting above a mobile interior that responds to tidal forces with remarkable flexibility. Saturn also influences Titan from far beyond its surface. Surrounding the giant planet is a vast magnetosphere, a magnetic environment extending deep into surrounding space. For much of Titan's orbit, this magnetic shield absorbs or redirects much of the incoming solar wind. The continuous stream of charged particles flowing outward from the Sunday. Cassini observed that whenever Titan briefly traveled beyond this protective region, the atmosphere experienced greater erosion. Without Saturn's magnetosphere, the moon would lose atmospheric gases more rapidly over immense spans of time. If you stood beneath Titan's orange sky, Saturn would dominate the heavens. Its disk would appear roughly 11 times wider than Earth's full moon. Instead of a distant point of light, you would see an immense banded globe occupying a substantial portion of the sky. Stretching across it would be an elegant line formed by Saturn's rings. Seen nearly edge-on from Titan, they would resemble a narrow luminous band crossing the darkness rather than the broad arcs familiar from spacecraft photographs. The relationship between planet and moon continues to evolve. In 2020, researchers analyzing Cassini observations concluded that Titan is slowly drifting away from Saturn at approximately 4 inches each year, nearly 100 times faster than earlier models predicted. Long ago, Titan almost certainly orbited much closer, where stronger tidal forces could have driven even greater internal heating and more vigorous geological activity. Some astronomers also suspect Saturn's magnificent rings originated when a moon with a composition resembling Titan ventured too close and was torn apart by tidal forces. If that picture proves correct, Titan endured where another world did not. It retained its atmosphere, preserved its chemistry, and continued its long journey around the giant that helped shape nearly every chapter of its remarkable existence. Imagine pressing pause on everything we now know about Titan and returning to the late 1990s. The picture becomes remarkably sparse. When Cassini lifted away from Earth in 1997, humanity knew Titan possessed a dense atmosphere, endured intense cold, and contained methane. Beyond those broad facts, the moon remained hidden. Its surface had never been observed directly through the orange haze, not in visible light or in any wavelength capable of revealing its landscape. That uncertainty began to disappear in 2004. After a journey lasting 7 years, Cassini reached Saturn and delivered the first close radar views of Titan's concealed terrain. Mountains, plains, and unfamiliar patterns emerged where only speculation had existed before. A year later came another milestone. The Huygens probe descended through the atmosphere and became the first, and still the only, spacecraft to reach Titan's surface, transforming an unseen world into a place with stones, channels, and horizons. The discoveries accelerated. In 2006, Cassini confirmed that the dark regions near Titan's poles were genuine lakes filled with liquid hydrocarbons, establishing the only stable bodies of surface liquid known beyond Earth. 2 years later, observations of Ontario Lacus identified ethane within one of those lakes using Cassini's infrared spectrometer. Titan had progressed from an indistinct orange sphere to a world with a functioning hydrological cycle built from methane and ethane rather than water. Then came results that challenged expectations in entirely different ways. During 2010, independent research teams reported the unexplained depletion of hydrogen near the surface and unexpectedly low amounts of acetylene where atmospheric chemistry predicted it should accumulate. 2 years afterward, measurements of Titan's tidal flexing confirmed the presence of a global subsurface ocean beneath the frozen crust. In 2013, the appearance and disappearance of radar-bright features in Ligeia Mare introduced the enduring mystery known as the Magic Islands. The pace continued. During 2017, astronomers using the Atacama Large Millimeter Array detected abundant acrylonitrile in Titan's atmosphere, while researchers demonstrated that this molecule could assemble into theoretical membranes capable of remaining stable within liquid methane. By 2020, analysis of Cassini's observations revealed that Titan is receding from Saturn approximately 100 times faster than earlier models had predicted, reshaping ideas about the Moon's long evolutionary history. A striking pattern connects every stage of this timeline. The immense dune fields were unexpected. The concentration of lakes near the North Pole surprised researchers. The rapid orbital expansion challenged existing theories. Even the abundance of acrylonitrile exceeded what many anticipated. Again and again, Titan proved more inventive than the models built to explain it. In less than 25 years, our understanding has expanded from an orange moon hidden beneath haze to a dynamic world with weather, seas, a concealed water, ocean, chemistry capable of producing amino acids, plausible ingredients for unfamiliar cell membranes, and atmospheric puzzles that remain unresolved. We have not reached the end of Titan's story. You and I are living through the middle of one of planetary science's fastest unfolding chapters, with each answer revealing another layer still waiting to be understood. Picture yourself standing on Titan for a moment. The greatest danger would not come from crushing pressure or intense radiation. It would come from the cold and from the simple absence of breathable oxygen. In several surprising ways, Titan presents engineering challenges that differ sharply from the familiar image of an airless, hostile moon. The atmosphere is one example. At approximately 1/4500 times Earth's sea level pressure, Titan does not demand the kind of fully pressurized spacesuit required on Mars. Instead, a visitor would need a heavily insulated protective garment supplying oxygen while preventing body heat from escaping into the surrounding environment. In many respects, The design resembles an extremely sophisticated hazardous materials suit more than the bulky pressure suits associated with lunar exploration. The comparison becomes even more striking alongside other worlds. Mars possesses only about 1% of Earth's atmospheric pressure, making a complete pressure suit essential. Venus presents the opposite extreme, with atmospheric pressure around 90 times greater than Earth's and surface temperatures approaching 900 degrees Fahrenheit. Conditions there remain beyond the reach of practical human exploration using technology expected in the near future. Titan occupies an unusual middle ground where pressure itself is surprisingly manageable. Temperature remains the defining obstacle. Surface conditions average roughly minus 290 degrees Fahrenheit, demanding extraordinary thermal protection. Yet engineers on Earth already work routinely with cryogenic systems, technologies designed to handle extremely low temperatures. Extending that expertise into permanent settlements would be an immense undertaking, although the underlying physics is already familiar. Radiation offers another unexpected advantage. Titan orbits beyond the most intense portions of Saturn's radiation belts. Combined with the Moon's thick atmosphere, this location provides meaningful protection against energetic particles arriving from space. Measurements indicate that the radiation environment at Titan's surface is gentler than conditions experienced on the surface of Mars, reducing one of the most persistent hazards facing future explorers. Power generation would require a different strategy. Sunlight reaching Titan is roughly 100 times weaker than what Earth receives, leaving solar panels with very limited usefulness. Reliable electrical power would instead depend upon nuclear systems, similar to the radioisotope generators that have successfully operated deep space missions for decades. Such generators convert heat released through radioactive decay into electricity, providing dependable energy regardless of weather or daylight. Titan's atmosphere also contains another practical resource. Nitrogen makes up the overwhelming majority of the surrounding air and could serve directly as the inert component within a human habitat. Oxygen would still need to be manufactured, most likely by separating it from water through electrolysis, a process that uses electricity to split water into hydrogen and oxygen. Movement across Titan could become surprisingly graceful. Dense air combined with low gravity makes powered flight remarkably efficient. Dragonfly demonstrates that principle on a robotic scale, and the same physics suggests future explorers might travel using compact rotor systems rather than relying entirely on wheeled vehicles. No agency is preparing to send people to Titan anytime soon. The journey would still require years in transit and demand technologies extending well beyond current human missions. Yet, once you imagine arriving, Titan becomes less a place of impossible extremes and more a destination that quietly challenges our assumptions about where human beings might someday endure beyond Earth. Some worlds tell us what the solar system became. Titan may instead show us what one world once was. Planetary scientist Jonathan Lunine has often described Titan as a chemical fossil of the early Earth, preserving processes that our own planet left behind billions of years ago. Rather than serving as an imperfect copy, Titan offers a remarkably intact record of chemistry that Earth has almost completely erased through the long success of life itself. If we could visit Earth approximately 4 billion years ago, we would encounter an atmosphere dominated by nitrogen, filled with active organic chemistry, containing abundant liquid water, and almost entirely lacking free oxygen. Chemists describe such an environment as reducing, meaning it favors the formation and preservation of complex carbon compounds rather than rapidly breaking them apart through oxidation. Those same broad classes of organic molecules continue to form naturally across Titan today. Earth's modern atmosphere looks dramatically different because life transformed it. Photosynthetic organisms gradually released oxygen over immense spans of time, culminating in what scientists call the Great Oxidation Event approximately 2,400,000,000 years ago. Remove every living organism from Earth. Wait long enough for biology's influence to disappear, and the atmosphere would slowly drift towards something chemically much closer to Titan than to the world we know today. The greatest distinction between these two worlds is surprisingly simple. Earth formed close enough to the Sun for liquid water to remain stable across its surface. Titan circles the Sun at a distance of approximately 886 million miles, where average temperatures remain roughly 260 degrees Fahrenheit, colder than the freezing point of water. The chemistry is strikingly familiar. Temperature changed the outcome. Imagine moving Titan inward until it occupied Earth's present orbit. Over geologically brief timescales, methane seas would vanish while liquid water spread across the landscape. The atmosphere and surface would begin interacting in entirely different ways. Organic compounds already present across the moon would encounter stable liquid water, bringing together ingredients that many researchers consider essential for prebiotic chemistry, the network of chemical reactions believed to precede the emergence of living systems. That possibility explains why Titan matters far beyond the search for present-day life. It functions as a natural laboratory where scientists can investigate the steps connecting simple molecules to increasing chemical complexity. Earth almost certainly passed through a comparable stage, but 4 billion years of evolving ecosystems have recycled, transformed, and buried nearly every direct trace of those earliest reactions. Every forest, ocean, bacterium, animal, and human being has contributed to rewriting Earth's original chemical landscape. Generation after generation, life consumed existing molecules and replaced them with new ones. The primordial record became increasingly difficult to recover. Titan never experienced that overwhelming biological transformation, leaving many of those ancient processes continuing in view rather than hidden beneath countless layers of later history. Seen from that perspective, Titan becomes something far greater than an unusual moon orbiting Saturn. You are looking at the closest surviving example of a world resembling Earth before biology reshaped an entire planet, preserving a chapter of planetary history that our own home can no longer show us directly. Few places force us to consider two separate definitions of habitability at the same time. Titan does exactly that. As we gather together, everything explored so far, one realization begins to stand apart. We are no longer asking whether a single environment might support life. We are examining two fundamentally different environments on the same moon, each presenting its own independent path toward biology. The first possibility lies across Titan's surface. Here, lakes and seas of liquid methane offer conditions unlike anywhere else we have observed. Researchers have proposed organisms using liquid methane instead of water as the solvent for chemistry, drawing hydrogen from the atmosphere, consuming acetylene as an energy source, and releasing methane as a metabolic product. Such organisms would function at approximately -290 degrees Fahrenheit, relying on chemical processes that differ profoundly from every living system known on Earth. Far below that frozen landscape, another possibility waits beneath layers of water ice. Measurements collected during the Cassini mission indicate a global ocean extending roughly 30 to 60 miles below the surface. In that hidden reservoir, liquid water could remain in contact with a rocky interior warmed by tidal heating. Those are conditions already familiar to astrobiologists because they resemble environments on Earth where microbial communities thrive around hydrothermal systems, drawing energy from geology rather than sunlight. These are not competing versions of the same hypothesis. They are separate scientific questions with different solvents, different temperatures, different energy sources, and potentially different biological rules. One explores whether life can emerge in liquid hydrocarbons. The other examines whether ordinary water-based biology could survive beneath an icy shell. Titan presents both questions simultaneously, making it unlike any other destination yet discovered. The hidden ocean naturally invites comparison with Europa, another ocean world regarded as one of the National Aeronautics and Space Administration's highest priorities in the search for extraterrestrial life. If water, rock, and sustained energy make Europa compelling, Titan deserves similar attention. Its ocean may offer many of the same essential ingredients while existing beneath an entirely different planetary environment. The methane lakes remain even more remarkable because no comparable setting exists elsewhere in the solar system. Nowhere else do we observe stable, liquid hydrocarbons covering the surface, while complex organic chemistry continues to build naturally and atmospheric measurements reveal unexplained chemical patterns that remain underactive. Investigation. Titan stands alone in presenting that combination. Suppose for a moment that both environments eventually prove inhabited. The implications would extend far beyond a single moon. Surface organisms living in methane and subsurface organisms living in water would almost certainly share no common ancestor. They would represent two independent origins of life developing under different chemical conditions while occupying different regions of the same world. That possibility reaches beyond Titan itself. Every estimate of how common life may be throughout the universe depends, in part, on understanding how often chemistry can cross the threshold into biology. Titan may become the place where we discover that the answer is greater than one. Long before Titan entered this story, astronomers were already wrestling with one of the deepest questions in science. It is known as the Fermi paradox. If intelligent civilizations should arise throughout a universe approximately 13.8 billion years old, why have we detected no unmistakable evidence that any of them exist? Given enough time, countless societies could have spread across the Milky Way. Yet when we listen, the galaxy appears remarkably empty. As we look at Titan, that question begins to shift in an unexpected direction. The paradox itself remains, but one of its underlying assumptions becomes less certain. Much of our search for life has centered on worlds where liquid water can exist at the surface. That narrow region around a star, often called the habitable zone, has shaped decades of exploration because every known organism on Earth depends upon water. Titan invites us to consider a broader possibility. If biology can operate in liquid methane, then water may not be the only solvent capable of supporting living systems. Methane remains liquid between approximately minus 296 and minus 258 degrees Fahrenheit, temperatures common throughout the distant reaches of planetary systems. Suddenly, worlds once dismissed as permanently frozen become scientifically interesting for an entirely different reason. Many of the galaxy's most common stars are small, cool stars that emit far less energy than our Sunday. Around them, cold environments are expected to be abundant. Beyond those stars, and even around larger ones, icy moons and distant planets may spend billions of years covered with hydrocarbon seas rather than oceans of water. If chemistry similar to Titan's can support life, then the number of potentially inhabited worlds could increase dramatically. But that possibility does not solve the Fermi paradox. It may deepen it. Imagine life developing in an environment where chemical reactions proceed at an extraordinarily slow pace, powered by unfamiliar metabolic pathways instead of abundant sunlight. Such organisms might remain microscopic for immense spans of time. They may never construct machines, never transmit radio signals, and never alter their world in ways visible across interstellar distances. They would still be alive, yet entirely absent from the kinds of searches humanity has conducted. Carl Sagan appreciated this possibility long before the Cassini mission transformed our understanding of Titan. During the final years of his life, he argued that this moon deserved a central place in astrobiology because it challenged assumptions carried over from Earth's singular example. He passed away in 1996, 1 year before Cassini began its journey, never seeing the discoveries that would strengthen many of those questions. Perhaps, then, the deepest lesson Titan offers is not simply whether we are alone. It asks how many fundamentally different forms of life nature can produce, each shaped by its own chemistry, environment, and history. If several answers exist, they may never recognize one another across the immense distances of space. We may share the universe with countless living worlds, each following a biological story so different that none of them ever realizes the others are there. Imagine the first stream of data arriving from Dragonfly after it begins exploring Selk Crater. The instruments complete their measurements, transmit their findings across the solar system, and those signals reach researchers on Earth. What happens next is not a race toward celebration. It is the beginning of the most careful scientific investigation ever conducted. Suppose Dragonfly returns evidence that meets the standard definition of a biosignature, an observable feature more readily explained by biology than by non-living chemistry. That evidence could include carbon isotope ratios characteristic of metabolism, molecular patterns too organized for known abiotic processes, or microscopic structures consistently resembling cellular organization. None of those findings would be accepted in isolation. Every measurement would be examined repeatedly, compared against laboratory experiments, challenged by independent teams, and tested against every plausible geological explanation. You can expect extraordinary caution. Planetary science remembers earlier claims that failed to withstand later scrutiny. In 1996, researchers announced possible fossil evidence within the Martian meteorite known as Allen Hills 84001. The announcement transformed public discussion, but subsequent studies offered competing explanations, and no scientific consensus concluded that the meteorite contained proof of life. That experience continues to shape how extraordinary discoveries are evaluated today. If, after years of examination, every alternative explanation failed, the consequences would extend far beyond Titan itself. The conclusion would not simply be that another world hosts living organisms. It would demonstrate that life originated independently at least twice within a single solar system. Earth and Titan followed profoundly different chemical paths, yet both crossed the boundary, separating chemistry from biology. That realization would alter the statistical picture of the universe. For decades, scientists have debated whether life's emergence was an exceedingly improbable event or a natural outcome whenever suitable conditions persist long enough. Two independent origins in one planetary system would strongly support the second possibility. Life would appear less like an extraordinary exception and more like a recurring consequence of chemistry operating under favorable conditions. Our understanding of Earth's own history would also change. Rather than viewing our planet as the singular birthplace of biology, we would recognize it as one example among many possible beginnings. The origin of life would become less a question about one remarkable world and more a question about universal chemical processes repeated wherever the necessary ingredients, energy sources, and environments come together. That shift reaches beyond astronomy. It changes how we define our place within the cosmos. Earth would remain uniquely meaningful as our home, yet no longer stand as the universe's only known cradle of living systems. Instead, it would join a larger family of worlds where matter organized itself into something capable of growth, adaptation, and persistence. Seen from that perspective, Titan represents more than a destination awaiting exploration. It represents a test of one of humanity's oldest assumptions. If the evidence ultimately confirms a second origin of life, the greatest discovery will not be that Titan is inhabited. It will be that the universe has been capable of creating life all along. Lift your attention away from Titan for a moment and consider the broader pattern emerging beneath every discovery. The farther we have traveled through this journey, the less Titan appears to be an isolated curiosity. Instead, it has become a reminder that the ingredients composing distant moons and the ingredients composing you belong to the same cosmic story. Every atom in your body was forged long before the sun existed. Carbon formed within ancient stars. Nitrogen emerged through stellar fusion. Oxygen was created in massive stellar interiors before being scattered across the galaxy when those stars reached the ends of their lives. The material that eventually became Earth, Titan, and every living organism originated from those earlier generations of stars. Look at the air around you. Approximately 78% of Earth's atmosphere is nitrogen. Titan's atmosphere is even richer, composed of roughly 95% nitrogen. The proportions differ, yet the element itself does not. Nitrogen remains nitrogen wherever it exists, obeying the same physical laws, whether drifting above Titan's frozen plains or passing through your lungs with every breath. The same connection extends to carbon. Titan's atmosphere continuously manufactures complex organic compounds that settle across its surface as tholins, complex organic molecules produced when simple carbon and nitrogen compounds are energized by radiation. Those molecules are chemically distinct from the proteins within your body, yet the carbon atoms themselves are no different. Nature assigns no special identity to an atom because it resides within a brain instead of a dune. The universe treats both according to the same rules. That is not poetic language. It is a statement about physical reality. The chemistry unfolding across Titan follows the same underlying principles that govern every reaction inside your cells. Electrons arrange themselves according to identical quantum laws. Chemical bonds form and break through the same forces. What changes are the surrounding conditions. On Earth, liquid water guides the reactions. On Titan, liquid methane may guide an entirely different network of chemistry under temperatures approaching minus 290 degrees Fahrenheit. As we compare these environments, a broader picture begins to emerge. The universe does not favor one chemical pathway above every other. Where liquid water persists, water chemistry unfolds. Where liquid methane remains stable, methane chemistry becomes possible. Elsewhere, entirely different combinations of pressure, temperature, and available elements create chemical landscapes unlike either world. Physics provides the framework. Local conditions determine the outcome. From that perspective, life becomes easier to describe without becoming less extraordinary. It is matter organized into a self-sustaining, self-replicating chemical system capable of maintaining itself against its surroundings. On Earth, that organization produced forests, oceans, animals, and people. On Titan, we are still asking whether chemistry has taken even the first irreversible step toward that same destination. Seen this way, Titan becomes more than another distant moon. It reminds us that the boundary separating living and non-living matter is written using the same atoms everywhere. Wherever the right ingredients, energy sources, and environments come together, the universe already possesses everything required to begin the experiment again. Think about how long Titan existed before anyone knew it was there. For approximately 4.5 billion years, that distant moon completed orbit after orbit around Saturn without a known observer anywhere in the universe. As far as our evidence can tell, its rivers flowed, its clouds gathered, and its chemistry unfolded without ever becoming part of another mind's understanding. For most of Earth's own history, there was no creature capable of asking what wandered across the night sky. Dinosaurs lived beneath the stars for roughly 165 million years, yet there is no reason to believe they wondered about moons circling distant planets. Much later, our own species began looking upward. Curiosity emerged gradually. The sky transformed from a ceiling of lights into a place that invited explanation. Titan entered that story only 371 years ago, when Christian Huygens first recognized it as a tiny point of light beside Saturn. 82 years ago, astronomers confirmed that this remote moon possessed a substantial atmosphere. Only 21 years ago did humanity finally see its hidden surface through the eyes of the Cassini mission and the Huygens probe. The interval between complete ignorance and detailed exploration occupies little more than 2 decades. Within those years, our understanding changed with astonishing speed. Titan ceased to be a blurred orange sphere. It became a world of methane rainfall, broad hydrocarbon seas, migrating dunes, a buried ocean of liquid water, and atmospheric chemistry capable of assembling remarkably complex organic molecules. It revealed amino acid precursors, abundant membrane-forming compounds, and puzzling chemical patterns that remain without definitive explanation. Each discovery expanded the moon without changing its distance. The Huygens probe remains there today. Its instruments no longer operate, yet the small machine still rests where it landed, surrounded by rounded stones of water ice within an ancient methane river channel beneath an amber sky. Nothing is expected to recover it. No planned mission will revisit that landing site. Season after season will pass across Titan, while the probe slowly becomes another object shaped by the environment it came to study. Over approximately the next 52 Earth years, Titan will experience 7 more seasonal transitions. Winds may gradually cover parts of the probe with organic sediment. Chemical reactions will continue at their deliberate pace. The landscape will keep changing whether another visitor arrives or not. Time remains abundant there. Its scientific life on the surface lasted only 72 minutes. During that brief interval, Huygens transmitted measurements, images, and atmospheric data across approximately 886 million miles of space. Those signals permanently altered humanity's understanding of the outer solar system. The duration was brief. The consequences continue. There is something remarkable in that relationship between distance and knowledge. You do not need to stand upon another world to learn from it. Careful instruments, patient observation, and disciplined reasoning can bridge expanses that seem impossible to cross. The universe rarely announces its deepest truths. Instead, It offers faint signals, waiting for a civilization willing to build the tools, perform the mathematics, and listen long enough for understanding to arrive. There is value in recognizing the boundary between what we know and what still lies beyond measurement. That boundary is not a failure of science, it is a map of where discovery is waiting. As we arrive here together, you can see Titan less as a solved destination and more as a world whose greatest revelations may still be ahead. Despite decades of remarkable progress, only about 67% of Titan's surface has been mapped in meaningful detail. Roughly one-third remains unseen beneath the limits of our observations. Every unmapped valley, shoreline, and plain represents terrain that no instrument has yet examined closely. The picture we have assembled is extraordinary, yet it is still incomplete. Our direct experience of the surface comes from exactly one location. The Huygens probe descended through the atmosphere and landed safely in a single dry river channel on a moon whose total surface area exceeds the combined land area of Earth by roughly 70%. Imagine attempting to understand every continent on Earth after visiting only one small clearing. That is the scale of the challenge before us. Many of Titan's most compelling environments have never been touched. No spacecraft has floated across its methane seas. None has collected liquid from those lakes for laboratory analysis. We have never drilled beneath the frozen crust or sampled the hidden ocean inferred from precise orbital measurements of tidal deformation. Everything we understand about that buried sea comes from observing how Titan responds to Saturn's gravitational pull rather than from direct exploration. Several of the most intriguing scientific puzzles remain unresolved. The hydrogen and acetylene anomalies, reported in 2010, have never been investigated by a dedicated surface mission. The changing features called the Magic Islands within Ligeia Mare still lack a definitive explanation. The source that continually replenishes atmospheric methane remains uncertain. Even the detailed composition of the subsurface ocean and the structure beneath it remain subjects of careful inference rather than direct measurement. These are foundational questions. Each one bears directly upon our understanding of Titan as an active world and upon the possibility that unfamiliar forms of chemistry may be unfolding there today. The absence of complete answers does not diminish the evidence we possess. Instead, it defines the next steps that careful investigation must take. Planetary exploration unfolds across generations. Years pass between a mission's earliest proposal, its launch, its arrival, and the gradual return of scientific results. Choices made by engineers, scientists, and governments today will shape what humanity understands about Titan in the middle of this century and well beyond. Every approved mission extends the reach of every previous one. Seen this way, Titan is neither an ancient mystery nor a completed chapter. It is an unfolding record of discovery, stretching backward across 4.5 billion years while continuing forward through the lifetimes of people alive today. You are not standing at the beginning of that story, and you are certainly not standing at its end. You are living within the middle of humanity's first real encounter with one of the most remarkable worlds in our solar system. Consider, for a moment, what it took for this story to become possible. We began on a single world, beneath one atmosphere, with no knowledge that another distant moon carried rivers, rain, seas, and perhaps chemistry approaching the threshold of life. Across countless generations, we learned to observe, to calculate, to build, and finally to send a machine approximately 886 million miles into the outer solar system. There, it revealed a place that echoes familiar patterns while remaining profoundly different. Nothing about that achievement was inevitable. Intelligence alone does not guarantee patience measured across decades. The Cassini mission was designed by engineers and scientists who understood that many of them would retire before the spacecraft reached Saturn. Some would never see its final discoveries. Others who now examine its measurements were children when the mission began. Knowledge continued because one generation chose to leave questions unfinished for the next. That continuity reaches much farther back. In 1655, Christian Huygens identified a faint companion circling Saturn. Nearly 3 centuries later, in 1944, Gerard Kuiper detected methane within Titan's atmosphere. During the 1970s, Carl Sagan demonstrated how complex organic compounds called tholins could form under titangent-like conditions, and he argued that this distant moon deserved careful exploration. Cassini launched in 1997. The Huygens probe reached the surface in 2005. The Dragonfly mission is scheduled to launch in 2028. Across approximately 373 years, each generation inherited a question, improved upon it, and passed it onward. No individual could witness that entire chain, yet every discovery depended upon those that came before. Scientific understanding grows less like a single breakthrough and more like a long relay, with each traveler carrying the same light a little farther into the unknown. The questions Titan presents are ancient. Where does life begin? What conditions allow matter to organize itself into something that grows, changes, and persists? Is Earth unusual, or simply one example among many? Long before telescopes, people asked these questions beneath open skies. Today, we ask them again through spectroscopy, orbital mechanics, precision engineering, and robotic exploration. The language has changed, the curiosity has not. Perhaps that is the most remarkable transformation of all. We no longer rely only upon imagination to explore distant worlds. We can test ideas against measurements gathered across the vastness of space. Instruments extend the reach of thought, allowing evidence to replace assumption while leaving wonder entirely intact. You and I are made of the same atoms that built Titan, Saturn, and every star that came before them. Those atoms eventually assembled into minds capable of asking where they came from and what else exists beyond their birthplace. Whether awareness carries any deeper significance is not a question Titan can answer. Yet it invites us to keep asking. For billions of years, the chemistry, the rainfall, the hidden ocean, and every unexplained pattern unfolded beyond Earth's horizon. They continued whether anyone observed them or not. Then, at last, a curious species looked outward, crossed the darkness, and found them. Imagine yourself standing upon Titan for just a single moment. Around you stretches a landscape unlike any on Earth, yet built from familiar elements arranged in unfamiliar ways. Above, the sky glows with a deep amber color that never becomes the clear blue we know. It is neither the darkness of open space nor the brightness of a sunny afternoon. Instead, the haze softens every horizon beneath a distant sun whose light arrives after crossing nearly 900 million miles, bringing illumination with very little warmth. High overhead, Saturn dominates the heavens. Its banded globe appears immense, many times wider than our own moon appears from Earth. The rings, viewed almost edge-on from Titan's equatorial regions, become an elegant line of light extending across the sky. Over approximately 15.9 Earth days, that magnificent sight changes gradually, reminding you that even the largest worlds remain in constant motion. The atmosphere presses gently against you with about 1 and 45 hundredths times the pressure experienced at Earth's sea level. You would notice the difference without struggling against it. Every movement meets slightly greater resistance. Every sound, if there were one to hear, would travel through denser air. Flight would become easier. Falling would become slower. Even ordinary motion would belong to another world. Far beyond the horizon, methane clouds may already be gathering above the northern seas. Somewhere, broad drops could be descending through the orange atmosphere, feeding rivers that slowly reshape channels carved into bedrock made of frozen water. Those valleys have been changing for hundreds of millions of years, following cycles that began long before complex life appeared on Earth. Their history continues whether anyone observes it or not. Beneath the dark surface of those seas, chemistry proceeds according to the laws that govern every atom in the universe. Perhaps those reactions never organize into anything beyond complex molecules. Perhaps they do. We still cannot say. That uncertainty does not represent weakness in scientific understanding. It reflects the simple honesty of standing at the edge of available evidence. Titan has existed for approximately 4.5 billion years. Humanity has known of its existence for only 371 years. We have begun exploring it for just over 2 decades. Against those timescales, our knowledge remains wonderfully young. Beyond Titan lies an even greater perspective. The observable universe contains approximately 200 billion to 400 billion galaxies. Within those galaxies are hundreds of billions of stars, many accompanied by planets and moons. Some almost certainly possess thick atmospheres. Others may shelter hidden oceans beneath frozen crusts. Still others may host unfamiliar chemistry unfolding across immense spans of time. We have examined one remarkable moon with care. It has rewarded every careful question with discoveries beyond expectation. As for the countless worlds that remain unseen, we simply have not looked yet. That may be the most enduring truth in planetary science. The greatest frontier is not only the answers waiting to be found, but the extraordinary number of places where curiosity has yet to arrive. Long before any living cell emerged on Earth, the universe had already begun its patient work. Across immense stretches of space, matter gathered, separated, collided, and combined. Carbon met hydrogen. Nitrogen encountered energy. New molecules formed, broke apart, and formed again. No audience witnessed those reactions. No purpose guided them. Chemistry simply unfolded wherever the laws of nature allowed it to continue. That process never belonged to our planet alone. Within cold molecular clouds drifting between stars, atoms assembled into increasingly complex compounds before planets even existed. Comets carried organic molecules across young planetary systems. Thick atmospheres transformed sunlight into unfamiliar substances. On distant moons wrapped beneath layers of haze, reactions continued through spans of time almost beyond imagination. Everywhere conditions permitted, the universe kept experimenting with the same handful of elements. Seen from this perspective, life becomes part of a much larger continuum. Before there were organisms, there was chemistry. Before there were ecosystems, there were molecules exchanging energy and forming new structures. A living cell represents an extraordinary level of organization, yet every atom within it obeys the same physical laws that govern a cloud of gas or a frozen sea beneath an orange sky. The distinction lies in arrangement, persistence, and the remarkable ability to reproduce. Titan draws our attention because that ancient chemistry remains active today. The complex organic substances known as tholins continue to form within its atmosphere before settling across the surface. Methane circulates through clouds, rivers, lakes, and seas in a complete planetary cycle. Acrylonitrile, a molecule capable of forming flexible, membrane-like structures under Titan conditions, has been detected in meaningful abundance. The unexplained patterns involving hydrogen and acetylene remain part of the scientific record, inviting careful investigation rather than immediate conclusions. Whatever process underlies those observations has continued for far longer than multicellular life has existed on Earth. Several environments on Titan provide opportunities for chemistry to persist across immense spans of time. Hydrocarbon lakes remain stable near the surface. A hidden ocean of liquid water almost certainly exists beneath the icy crust. Temporary pools of liquid water may appear after large impacts, melt portions of the frozen ground before freezing once more. Each setting offers different ingredients, different temperatures, and different pathways through which molecules can become increasingly complex. Hundreds of millions of years pass, then billions. Chemistry never becomes impatient. Every reaction builds upon countless earlier reactions, preserving only what remains stable under local conditions. If organization eventually emerges, it does so gradually, without spectacle, through ordinary physical processes repeated beyond counting. As we reflect upon Titan, the question begins to change. Instead of asking whether the universe possesses the ability to create life somewhere else, we begin asking how often chemistry reaches that threshold when given sufficient time. You and I happen to exist at a moment when those questions can finally be investigated with instruments rather than imagination alone. The remaining challenge is beautifully straightforward. We must continue looking with care, continue listening with patience, and allow the universe enough opportunities to reveal what it has been doing all along. There is a difference between imagining a distant world and knowing that it exists. Titan belongs to the second kind of truth. At this very moment, it circles Saturn, nearly 886 million miles away, carrying rivers, shorelines, clouds, rainstorms, and an amber sky above a landscape where rounded stones of water ice rest within an ancient river channel. A small probe still remains there, exactly where it completed its final transmission after 72 remarkable minutes on the surface. That place has not become less real because we are far away. It continues through its seasons, whether anyone watches or not. Methane clouds gather, lakes respond to changing weather, organic molecules drift downward through the atmosphere and settle across the ground. Beneath the frozen crust, a hidden ocean almost certainly endures, separated from the surface by many miles of ice. Everything we have learned points toward a world that remains active, dynamic, and unfinished. We still cannot say whether anything lives there. Perhaps the methane seas contain only chemistry. Perhaps the buried ocean shelters water-based organisms unlike anything we have yet encountered. Perhaps both environments are entirely lifeless. The uncertainty itself rests upon evidence rather than imagination. The unexplained hydrogen and acetylene measurements were recorded. Complex organic molecules have been detected. The atmospheric chemistry has been measured. The observations are genuine. Their ultimate meaning remains unresolved. That distinction matters. We are no longer asking an abstract question about life somewhere among countless stars. We are examining one specific world whose properties can be measured, tested, revisited, and explored again. Every future mission will build upon those observations, adding another small piece to a story that has unfolded across generations of scientific work. Titan and Earth began with the same raw ingredients. Carbon, hydrogen, nitrogen, oxygen, and countless other atoms were forged within stars that lived and died long before our sun was born. Gravity gathered those elements into different worlds. Temperature shaped what followed. On one world, liquid water dominated the surface. On another, liquid methane assumed that role beneath an orange haze. The underlying physics never changed, only the setting did. For 4.5 billion years, Titan has continued along its own path. Rivers have carved channels. Rain has fallen. Organic chemistry has unfolded without interruption across spans of time almost impossible to comprehend. Whether that chemistry has crossed into biology remains one of the most compelling questions humanity has ever asked. As you rest beneath Earth's familiar sky, you carry the same elemental heritage as that distant moon. The nitrogen moving through your lungs belongs to the same family of atoms filling Titan's atmosphere. The carbon within your cells is the same element drifting through its haze before settling across frozen ground. Nothing separates those atoms except time, temperature, and place. We are part of the same universe, shaped by the same laws, discovering ourselves one world at a time. Tonight, that understanding is enough. It reminds us that every careful observation expands the horizon of what it means to exist, and that somewhere beyond the darkness, Titan continues its ancient journey, patiently waiting for the next question we are ready to ask.